I haven't recorded this lesson yet, so I'm going to try not to screw this one up. We are talking about... Where is the... There's no label on these things? Okay. Were there labels on previous ones? Hold on. Yeah. Normally there's a label. I don't know what happened to this one's label. But we're talking about Lesson 10. Finally functional programming. Video at the top. A bunch of shit beneath that. Here we go. We're going to be talking about how my headphone cord is somehow twisted in a way that never seems to resolve itself, and it's driving me insane. But in addition to that, we will be talking about stitching together some of the things that we've done so far. We have learned about maps and other shit, and we are going to learn how to stitch those things together. So, just to give a recap of where we've been in this course so far, we have started with writing generators that were very straightforward, right? Basically just gates that process directly through the code. We moved to things like creating lists, which are sort of complex outputs. Things like creating... I want to make this slightly louder. Make it there. We moved to talking about recursion, before recursion we talked about conditionality and having branching outcomes based on some condition. We then talked about recursion, and most recently we've talked about, or begun to speak about, maps. In the last two lessons that we have here, we're going to start stitching those things together in ways that hopefully make it clear how you can use those tools together to accomplish some work. Hence the name, finally, functional programming. The fun in functional is capitalized in my initial draft. Isn't that clever? Fun, right? Right? All right. So as we say here, the generator that we're going to look at today is long, but it's not really that complicated. We're really trying to... I think we had a pretty hard lesson with Caesar Cipher over the weekend, and we're trying to now bring that back down to base level, make sure that we're clear on the concepts that we were utilizing there, and re-solidify your understanding of all the different tools that are available to you. Okay. Ayo. Yeah, how about that? I cracked myself up. I'm going to post some shit in chat here just so that I can have this at the bottom. Test. Alright, so now I can see that at the bottom of my screen if you say anything over in Twitch chat and I won't miss it. Okay, today we're going to build a generator that does something useful. We're going to make a length converter. So it's going to be able to convert between a lot of both useful and archaic and unknown and pretend measurements of length, including the smoot. I invite you to look up the smoot on your own. I won't get into the details because that would ruin the fun of it. But what we're going to be able to do is provide the generator with some input measurement unit, an output measurement unit. So we're going to be converting from to, and some value in the middle that will be the number of input measurements that we will be converting into the output measurement. The input measurement, the value of the input measurement is going to be given in single precision floating point notation. And we'll talk about that in just a minute, but if you are already aware of what that is, then you know what we're talking about. Alright, let's get started with the tools that we'll need to do this. The first of these is love. But after that, it's WhatPam. WhatPam is going to check an AND condition. So basically, it will take whatever tests you put inside of it. It's an indeterminate rune, so it can take as many tests as you want. And if all of those tests return true, then WhatPam will return true as well. And so we can take a look at that really quickly. So let's say we have WhatPam, and rather than test, we'll just give it some values, just so we can see that it's indeterminate in length. We're going to get a yes there. If any of these is a no, we will get a no. So this is checking to make sure that and for all of these conditions. Now we can replace these written out values with some condition, 1, 1, tis pal 2, 2 par, for instance, and those will prove to be true as well. We can go further with our code and we can say, like, suppose we have A is equal to the list pat of 1, 2, 3, 4, and we could do gosh, I'm going to keep saying that wrong. WhatPam, and equals, what should we do here? Snag, let's see, snag 2 A3. Oh, where did I do it wrong here? 2 of A should be 3, shouldn't it? What, Pam? Exactly. What's snag 2 of A? So that's right. Oh, yeah, duh. Okay, so complicated. Let's suppose we have a complicated formula in here, right? We are saying what, Pam? So if both of these things are true. The first of which is love. But the second of which is our snag of 2, the position 2 of A, is it equal to 3, which we know it is from here. And the second of which is A null, which it is not. And then we are doing the inversion of it using WhatsApp. Okay, and that should give us, oh no. Shouldn't that work? Yeah, there we go. It didn't like that notation. Okay, that's fine. So there we go. Point of this, right? This seems ridiculous and stupid and I'm wasting time. But the point is, we're going to use WhatPam to evaluate any series of conditions that we put inside of it. You could also write it in tall form, right? So you could have like WhatPam equals tis pal 1, 1 par, tis pal 2, 2 par, tis. So that would be the tall form. As you can see, indeterminate in its length. It takes as many hoons as you want. It returns either a yes if true or a no if false. Okay, spent enough time on that. One last thing he says as he lies to you. The shorthand notation is just Pam. So that's going to give you the same value. So you don't have to put the what. Okay, we're going to use that to check later on. We'll see that both of the measurements that we give in as the to and from measure, or the from and to measurements units, are ones that are in the generator, that are available to us. Okay, next, a stack tracing printf. You have seen this in the last lesson, sig bar, then some error message zap zap. That was in the Caesar cipher, and it was part of the, we can actually look at it. I think no, I don't have it, but it was where it checks for the length of the two tapes, and it makes sure that they're the same. So here. So this notation, if your lengths were not the same, it would give you an error message uneven lengths, and then crash the program, and give you a stack trace to that point. We're going to use that as well. We can see it in the dojo very easily if we just sig bar gap, whatever, gap, zap, zap. And we're going to get whatever error forward ride failed to execute. So if we put that in a longer generator, we're going to see some additional stack tracing, but that's effectively what it does. Note that you can put in a tape if you want to, or a chord, or a PATRS, or any number of values here. These are just pre-printed in the dojo for you to see so that you can trace your error. Okay, so we got WhatPam, we have sigbar and zap zap, which crashes the program if zap zap wasn't clear. Next, we have two more. The LessBuck rune. Now this is going to be one of the most interesting ones that we deal with today. And as I say here, it's kind of difficult to demonstrate in the dojo, but I think I actually wrote something this morning or yesterday. I don't remember. All the days blur together. And an endless. What do I have? Do I have it in the dojo? I do must have it in the dojo. I do not. Okay. So, alright, so I've written this like really stupid core up here, but you can see that it uses LessBuck. So this is going to tell us, or this is going to create for us a type. So the LessBuck rune creates types. You give a face to your type, just like list or PATUD or whatever map, right? These are molds that are available to you with their faces, right? And then you're going to use a buck rune to determine how you want to, how would you say this? Establish that type. So let's look at the definition of both of these. LessBuck. Where's the buck key? There we go. Okay. Less produces a structure arm. A structure is like a list or a map or whatever. You can do your own versions of these. That is the takeaway here. So there are some that are built into the type system of Hoon. There are also ways that you can produce your own structure arm using a variety of buck runes. Let us look at the structure expressions, which are the buck runes. So first look at the structure here. LessBuck, then your term, which is your name for it, so that's going to be typer over here, and then your specification for what that structure is going to be, which is here. So we haven't discussed what that will be, but if we look at the buck runes, all will become clear. All is klar. Okay. Buck what? Form a type from a union of other types. All that really means is that the new type called typer is going to be one of these these four PATRS values. So this is a union of types, a bunch of PATRS values that are available. If I want something to be a typer, it has to be one of these. Further, the normalizing factor of this, which is to say sort of the default version of this, is the first item in the list. The first item in P, which is this guy here. So it would be 1. It's a metaface. Yes? It's a Metatron. It's something like that. It's like yeah, I guess a metaface. I like that. It's not really like the face is a face. It's like it's a new type. Right. I guess you would say it like this. Like a list has a specific. So the question is, what exactly are we doing here? A list has a very specific definition, right? We have learned that a list is a null terminated series of nested cells, okay? Right? Like this. That's a list. A map is something else. An atom is something else. You can make constructs of types that you don't have. So suppose you want a type where the type is like TAS value, so TAS goes here, and a PATUD value here, right? This cell. So you could specify that type by saying, I'm going to return a cell of PATTAS, PATUD, right? But you could also declare this as a type itself and say, I'm going to return for you. Imagine, Minder, the reference for you here is a card, right? So suppose this is my suits and this is my face value. Like, forgive the fact that you couldn't do a face value with a PATUD, but, right? I can declare a type of card and specify that it's always going to look like this. And then when I'm writing other code that references cards, I don't have to type out this whole thing again. I can just go, this is a card. I'm going to give you a card here. I'm going to return a card. I'm casting my output as a card. Or you could then create a list of cards and call it a deck, and that could be a special type as well. So it's just shorthand for other types that could be construed using what's available to you immediately, but instead we're doing it in this more efficient way. Does that track? We're going to do it. Let's look at how this works in the dojo here. Okay, so my code is simple. My heart is pure. What is it? Clear eyes, cold hearts, can't lose. Something like that. Okay, so we have one arm of core called typer that's going to give us a type. Let's see what typer.core does. Okay, so nothing of use. There's probably a way to... Oh, that's interesting. It's actually normalizing to the last item. I think that this needs to be changed. So I'm saying here, give me the bunt value of typer, and it's giving me Alario, which is the fourth one in the list. But neither here nor there. It's not going to be super relevant. Okay, so typer is our type. Let's look at the arm confirm. It's going to take a PATRS. It's going to check to see if the PATRS passed in is of the type typer, and it will return a yes or a no. Very simple core here. So first we can do confirm.core, and since it's a raw gate and we haven't passed it an argument, it's going to show me that it's a raw gate, and you can see that right here. We should know this structure. We should know that this means that we're calling a gate without a sample. We can senhep it, right, which is the same as doing add 1 1. If we senhep add 1 1, same result. Okay, so we can senhep it, and we can say senhep gap confirm dot core gap 2, and we'll get a yes. Note these types here. This is what we're looking at. If we did 1, we get a yes. If we do Alario, we get a yes. But if we do 4, we get a no. So in this dumb core called core, we have created a type called typer, and we have created a checker called confirm that will confirm whether an input value to that gate is of the type established in typer. That's all that's going on there. And that's all you really need to know. And the simplest of, I was about to say the love joke again. The simplest of these types, type creators, or structure creators, that are the buck runes, is buck what, which allows you to create a structure from basically a series of examples. Yeah? Good? Great. So long and the short is we will be using LessBuck, and we can just show this. We will be using LessBuck to do two things. First of all, we've created a structure called allowed, and that is up here. Oh, I forgot that I changed this code. Let's look at it. Check if a noun is of a certain type. Yeah, like WhatTis does that. Maybe I'm not sure what your question is, because there's like WhatTis, WhatCat, WhatPat, right? Like noting that WhatTis can't work on atoms. It has to work on complex types. Tell me if I'm missing your question there. That's totally possible. Okay. Oh, I closed it. Oops. Why am I dropping frames? Unacceptable. I'm going to copy the code from the generator today so we can take a peek at it here. Just give me a second. Alright, so we have this allowed function here, this allowed arm, which is a LessBuck arm. So we're creating a type called allowed, and we're defining that type as the union of all of these. You may recognize these as measurements of length. Some of these are more fancy than others. My two favorites are the, where is it? The megalithic yard here, and the smoot. Two favorite measurements. In fact, we're going to convert smoots to megalithic yards to smoots. All right. So here we're going to use LessBuck to establish a type called allowed and define it as all of these different measurements that we have available to us, right? And those are represented in this map that we'll see later, but these are basically all the ones that I could be troubled to find conversion factors for. So that's pretty much what's going on there. You could add more if you wanted to. The second thing we're going to be doing with the type is using WhatTis to check if the input measurements from the initial gate, both the from measurement and the to measurement, are of types where we will have conversion factors. Because otherwise, we don't know how to convert from one measurement to another, right? So this program is only as smart as we are in terms of including the conversion factors to wit. All right. Last thing that we need to learn today. PATRS values, or single precision floating point numbers. So I think the shortest way to explain this is that computers can't do fractions just like second graders can't. They just don't fucking get it. And so you have to work with them basically in scientific notation, right? So you have to use whole numbers and then move the decimal around. And there's a couple of problems with that, right? Like, there are fractions that are irrational, that are repeating, that are, well, that's the same as repeating, but interminable, right? Like 1/3, right? That 1/3 can't really be, yes. That's reducible, though. But yes, why am I dropping frames again? I'm so mad. So mad about that right now. Better not drop frames again. Alright. It's going down again. If I'm dropping frames, let me know, okay? Because I'm pretty pissed about that. I'm like hardwired to a fucking... Bring it in. Okay, so the PATRS value is the way that we're going to handle fractions in Hoon and in computers in general. You may know from doing, like, I don't know if you've ever done this, but let's... So, like, have you ever done conversion factors in chemistry where you're trying to convert one measurement to another, right? Like this? This is what we're going to need to do to convert, yeah. This is what we're going to need to convert one measurement to another, right? Because they don't all uniquely or rationally divide into each other. And in order to do that, we will be using single precision floating point numbers. Basically, all that means is that we're going to have a 32-bit number to work with, and we can represent it as whatever our fraction is. We can represent it as a notation to the power of 10. So suppose we needed to represent, let's say 1/3, okay? So we could do all PATRS values will begin with point, and then they will have some number thereafter, and then another point if you want to provide more detail on the bits that you're providing. You can go up to 32 bits here, right? So we could have something like that. That's like 1/3, except for we know that 1/3 isn't 3 and 33%, or 3 and 33333 repeating. It's just 0.333 repeating, right? So then we can say error, or to the power of -1, right? So this is going to move the decimal place 1 to the left. It will print as same. It will give us 0.333 repeating. In that way, we could mul rs, and we'll see that this is how you use... a good note. The multiplication, addition, subtraction functions that you've learned so far, they don't work with RS values. There's a different series of mathematical operators that you can use on PATRS values. If you can figure out why in chat, I'll give you $1. Good luck. Why we need that? Okay, so let's say I want to get 1/3 of 6, right? So I could multiply 0.6.0, which is the PATRS value for 6, times 0.3.333 e to negative 1. Aha! And here is another curiosity of floating point mathematics. The other curiosity is that because we only have, yes, because it's Hoon, because we only have a certain number of significant figures, right? Or like, that's probably a misuse of that terminology, but a certain number of points of precision. When we do division, we get an approximate value. There's a whole website devoted to this. I'll paste the link in chat that kind of explains what's going on here. But as you can see, we are getting an approximation of 2. When we multiply 33% times 6, we get 1.99998, which is effectively 2. Okay, review what we've learned. We have learned WhatPam, which is just making sure that everything inside of it is true. We have learned how to crash with an error message, which isn't very complicated. We have learned how to create a type. The easiest way to create a type is to just put a buck or a buck what in front of a PAL-PAR surrounded series of types that you would want. So like if you think of it, so it's more specific and more precise. It's not even more specific and more precise. It's actually less precise. Like I say, this is just like a second grader who doesn't understand how to do fractions. So they have to make imprecise their calculations by reducing them to decimal notation. And because you can only contain a certain number of decimals, you can only have a certain level of precision. Now there are in fact 5 different types of floating points available to you in Hoon. So single precision floating points are what we have, 32 bits. Double is 64. Quad is 128. IEEE standard, which is like some electrical engineer standard, is some other value. I don't remember what. And then there's one other one that I don't recall offhand. But so you can get more and more precise, but you will never be able to divide 6 by 1/3 and get the precise 2 out that you want. Some values will work, but otherwise it's just going to give you a little bit of a rounding error. Okay. LessBuck type, use buck_what to establish a type surrounded by PAL-PAR and provide all these types that you want to unionize here. So you could think of it this way, Minder. This would not be the best way to do this, but if you wanted to establish every potential card notation that's available, you could be like, this is the club ace, and this is the club 2, and so on, right? So you could write all of those out. Again, that is not the best way to define cards, but that is something that you could do. Okay, and lastly, we've talked about single precision floating point numbers, PATRS atoms, and how to deal with them. Any questions about that before we turn to the generator proper? By the way, what did I bet you wouldn't be able to figure out? I don't remember now. Man, I totally forgot what I said. Oh well. Alright, let's look at the PATRS's input. Binary trees as well. Well, they're atoms, so they would be a leaf. Oh, yeah. Well, so I just gave it away, didn't I? Let me talk about that, because I think that's actually important. PATRS's are atoms, so they are represented as some arbitrary number cast into its own aura. So the let's just look at it this way. 1 in PATRS, right? That's not where I want to be. Down here. 1 in PATRS is just written as, so let's just create 1 PATRS 0.1. If I call 1, I get 0.1, which just means 1 in PATRS, okay? If I add 1 and 1, how's that happening? What's going on there? Anybody? In contrast, add 1, 1. That's right, Minder. So the PATRS is not stored. Let's just look at it. If we cast it as a raw atom, its value is, what is that? 1 billion? Is that 1 billion? 1,065,353,216. So that's just the atomic value at the position that references that PATRS value. And there's probably some reason why 1 is here and not some other number, and it probably has to do with how far up and down you can go. I don't know what... yeah, so like the smallest notation here is period 45 zeros, no, 44 zeros followed by a 1. Does that make any sense to anybody? Do you see what I'm saying there? The atomic value of a PATRS is not correspondent to the PATRS's denotation value. That is to say, 0.1, which is a PATRS, which means 1 in our brains, is not equal to the atomic value of 1 for a variety of reasons. Does that track for anybody? That's kind of complicated. It shouldn't terribly matter, but what you need to know is that if you're adding or if you're mathing with PATRS values, you will have a different series of functions available for you to do that. Oh, fantastic. Okay, so that actually does make sense. Fucking sick. Okay, let's look at the code and get into it. And you know what? I'm actually we'll start this way, and I'll save this too so that we can get the color coordination here. Is your amend once we go. Yeah, it's like absolute. It's like Fahrenheit versus Kelvin or something. You know what I mean? Like Kelvin, you can't have a point. Well, I don't know if this is true or not, but you can't have a partial Kelvin. You start at 0. You know what I mean? So you go 0, 1. It has to, just like with the floating points, they have to start at the bottom smallest decimal value that you can get with a 32-bit floating point and go all the way up to the top possible value. I hope that makes some sense. Okay. Let's look at the generator itself. Couple things to note immediately. We're starting with a gate that takes some arguments. We then have a TIS-gal that is going to... it's one hell of a TIS-gal. She's a real spunky one. The TIS-gal is going to compose two expressions inverted, the first of which will be processed after the second of these. So the first one is whatever hoon is right here, and we'll talk about what that does in a minute. The second of which is this core down here. So effectively, we will be opening our gate, then immediately storing this core in memory, and then doing some work that references that core. Because note that this isn't like a barcat or some other, or like a barhap or some other core that has an arm called buck that is calculated immediately. Instead, this is just some core that exists in the world, right? It's just there. is there for us to access. We'll be accessing parts of it up here. Okay, let's look at our gate. Our gate is going to take a from measurement as a PATRS. A number of those are like a value, so like the number of feet or the number of meters or whatever. And a to measurement, which will be our end point for our conversion factor. So we could convert from meters, one of them, to decimeters, and we would get something like 10. It'll probably be 9.999, but you get the idea. Okay. Again, we have the TISGAL that's going to hold this core in memory, and we'll switch the SIGBAR tape to a PATRS again. I could. Maybe I will. Maybe I won't. What are you going to do about it? I like that notation better anyway. Because that's what they do in the Hoon.Hoon library. Like, subtraction underflow is represented. I think it is. Let's see. Oh, they just... What are they doing there? Is that a chord? I actually don't know what that even is. Let's... Well, hold on. Now I have to know. Wait, that's not where I want to be. Oh, it's a leaf. See what they're doing here? Wait, so is that... Wait, that's not even the same error message. There we go. All right, well we'll change it to that. I like that. This doesn't change the rest of the generator. It's just fiddling around, but okay. Shake my head like an Etch-a-Sketch. Let's get back to it. So we have our from measure, or the number of them that we're going to convert, and our to measure, which is where we're going to convert to. We're going to compose this expression second, so let's first look at the core. The core, we have a couple of things going on. We have our allowed, which is, again, the type of all measurements that are allowed. Those go from inch to furlong to chain to megalithic yard to smoot and so on. There are metric ones at the end, but those ones are boring, so I didn't put them up front. We then have an arm called check. Check is going to take in two PATRS values. They are in fact the same PATRS values in the same faces, so these just drop down directly. And it's going to WhatPam to make sure that both of them are of the allowed type. So we have the whatTis here to check type against value. It will make sure it's one of these here. That way, if your user puts in something kooky that isn't quite right, or they spell foot with two U's, it will give them invalid measures, and they will know that they typed something in wrong. So check will return a yes or no based on whether both of these are true or if one of them is false. It's football. And then we have meters. Meters is going to do something fairly interesting here. So meters is going to take your from measurement here, so what you're converting from. So let's say that's kilometers. Okay, so you're going to punch in like sen kilo, because meters I just have with their prefix, but sen kilo, and then your value is like one of them. Okay, so it's going to take both your from measurement and your value. It's going to create a value called, or a face called factor 1, and we should know this notation here. This is, somebody write this out in long form, but I'll tell you what it's doing. It's looking for the key. It's looking for the value in the key position where the PATRS is whatever we put in, so kilo, in some map here. I want to see this in full notation, though. Somebody write it out in it doesn't have to be tall form, but wide form with the non-shorthand version. Yeah, that's it. That's it. Okay, so what it's doing is it's calling a gate from the door by replacing the map, the default map in there with some map that we have here. Here's a note. It's down here. We'll look at it in a second. That gate takes a key and returns the value at that position. We are calling that gate using senHep. That's what this notation is. Remember, add 1, 1 is the same as senHep add 1, 1. That's what we're doing here. We're just senHepping got by convert to map. And convert to map should be familiar to you as well. It is producing a map of PATRS values and PATRS values. So we use the my gate to construct a map from a null terminated list of ordered pairs. Here's our null termination. Here, all of these colheps are our ordered pairs. These are effectively just cells. We could also write them out as cells. I thought it looked a little prettier to do it this way. Okay. What are these conversion factors? Well, all of these conversion factors are based off of the meter. So everything, these are the conversions of 1 meter to whatever these other measurements are. Which means that here we are getting the conversion factor to convert whatever measurement we got in and the value of that measurement into meters by multiplying the value we got in by the conversion factor. So for instance, let's look at a decimeter. Where the fuck is a decimeter? Here, decimeter. You may know, if you're one of those clever Europeans, that 10 decimeters equals 1 meter, right? So we have this notation of 0.1 e negative 1, which is in human notation, 0.1. We can do like 0.1 times 10 is equal to 1. Therefore, we know that like this is the conversion factor of decimeters to meters. So if we got in meters, no, I'm sorry, if we got in decimeters, and we said we received 20 of them, and we multiplied, which is what we're doing up here, we're multiplying that conversion factor times the value, we would have gotten... You have to wonder why Liberia and Myanmar... There's a reason it turns out both Liberia and Myanmar are going through the process of metricization. Yeah, because we're the best one. We're the best. America. Go America. Alright, 20 times 0.1, which we know to be the conversion factor of meters to decimeters or decimeters to meters, would mean that we have 2. Right? And 20 decimeters, 2 meters. So, in the meters arm, we are simply getting our conversion factor and multiplying our value by it to convert whatever measurement we got in and its length into meters so that we can better use our table to convert into some outgoing measurement thereafter. Fairly simple. If we didn't do this, we'd have to have like all different sorts of conversion factors to use for like, oh, well, if I'm doing picometers to millimeters and I don't have a standard in-between factor, I have to figure out the conversion factor between pico and milli, right? Which is like awful. Okay, so that's why we convert to meters. Lastly, we have an output function, which does effectively the same thing. It's going to take in some RS value and out some TS value. So this is going to be the outgoing measurement. This will be the measurement currently in meters. It will check if the outgoing measurement is supposed to be meters, in which case it'll just print whatever it got out of meters, right? Because we've just converted to meters. We don't have to do anything else if what we want out is meters. So if we said I want decimeters to meters, it would convert decimeters into meters and then print that here. Otherwise, we will use divide, and we will divide our incoming value by, in this case, the conversion factor to the outgoing measurement. So if we had 1 meter coming in here, so we have 1 here, and our outgoing measurement is decimeters, we will divide 1 by 0.10, or by 0.1, which will result in 10, right? And that gives us how many decimeters are in a meter. Okay, so that's the arms. We have a type, we have a checker of types, we have a convert to meters, we have a convert from meters into something else, and lastly, we have the conversion factors of meters to all of these other dumb measurements. Let's look how we stitch it together in the first expression of the TISGAL. And before I do that, I will pause for any questions because I have been talking fast. Anybody? Like basically one smoot, I think. We'll see. So I'm okay. Let's actually do this math. First let me talk through how this works, and then we'll figure out how many smoots tall I am. We're casting our output as a PATRS value. All right. We're using what dot to form some test. If that test is false, we'll produce this line. If that test is true, we'll produce this line. The test is to return whatever the arm check is with the 2 measurements we got from the gate here going to it. And again, all that does is check to make sure that it's one of the measurements that we have conversion factors for. If it is, then we go to this line. Here we're calling output with the product of the meters conversion arm and our destination measurement. So basically what this is saying is convert from whatever measurement you got in and the value of it to meters, and then send the number of meters and the destination value to output to be converted into that many output measurements, whatever they are. Okay. And I actually have this saved as another generator. So let's say okay, so let's watch it in action, but first I gotta do some math. I'm like 5'7", so 5 times 12 plus 7. I'm 67 inches tall. So we can say you don't need to have leaf in. Oh. Well, there you go. Thank you. Inch 67 smoot. Oh no. 917. I don't know if you do. Hold on a second. I gotta see what I don't actually have this generator open like an idiot. Oh, this worked earlier today. Error at 917. I know. What did I do wrong? I don't know what I did. Did I take out tap? I thought tap was what was getting me back from a set. Flattens the set into a list. But we didn't want a list. That's what it was. Man, that sucks, because I had that working this morning. Well, it doesn't matter. Whatever. Yeah, I think you're right. I think it's, that's alright. I thought I did. Didn't I? Did I not get it working? I thought I did get it working from that typing. Oh, maybe I'm just remembering it wrong and saying I was just checking, because yeah. No, I gotcha. My bad. I remember now. Okay, so let's just go back up here. We'll just do it from the original code. 73. Oh yeah, and I forgot. It's going to do all this nonsense. And let's answer your question while we're at it. Do we need leaf here? I think we do. Oh no, I guess we don't. Or I don't know. Let's check it. Oh, sorry. Gotta call it with the PATRS. So 67 inches in PATRS notation would be 6.7 e to the 1. You could also just write it as 0.67. Yeah, like I'm dead nuts on one smoot tall. Let's try it with a false measurement. So, like, you know, the classic aunch. So I think you do need a leaf. Leaf plus. Let's get an aunch in here. There we go. Beautiful. Okay. Does it need an ace or a gap? No, I'm doing something wrong. What I was trying to do, long story short, is rather than writing this out, I was trying to read all the keys from the map and produce them here as ace separated, and I was failing to do that. So, what if you could just do turn? I don't know. I'd have to think of it. I remember what I did. What I did was I just had it check to see if it... I used has from by. So here, rather than using a type, I just had it check if... And you could even do it up here. I had it check if... like this. I'll show you. Yeah, okay, you get it. We don't need to go into it. Okay, but that's the long and the short of what we're doing here. Just to run through it one more time. We are getting our measurement in, our value in PATRS notation, our measurement out. We are checking to make sure both of those are valid against this list here. If they are not, we give an error message. If they are, we convert the first one and its value, these guys here, we convert them into meters. We then convert the meters into the destination measurement. That's all contained within this core, those arms here. And lastly, we have a map of conversion factors here. This is really pretty easy. It may seem weird and complicated right now, but if you look at this for an hour or two, I think it will be very clear what's actually going on. And please do just use the code that's in like the standard lesson, and don't try to follow me doing dumb stuff in it. Because our homework is going to be to first of all read the Magic 8-Ball, which will talk about some of the different things that we can do with PATRS values, and read about tree sets and maps here, some of the operations you can do. But the work that we want you to do is add to the generator the ability to convert some other measurement type and add some argument or figure out some other way. There's probably ways to do this where you're not adding an argument that indicates whether the measurements are of length or of some other thing like volume or force. Like I want to know how many horsepower are in a Newton. Does that make sense? Maybe. Again, you will further enforce that the from and to measurement of your types are strictly construed, and you're going to create a new map that handles your conversion method. So basically, you're going to write a second set of arms here, or you can reuse the ones that you got if you can think of a good way of doing that, to convert volume or mass or I don't know, temperature or something else. Okay? Alles klar? Jawohl. Alright. Mach schnell. Let's see what you can do. I will be here again tomorrow night, same time, same place, to go through this one more time. If any of this was confusing, please do join. I was going to say I hate it when I talk to myself here, but that's not really true. I don't mind talking to myself. Yeah, then we'll have homework help on Thursday and Friday. And then 1 week left in Hoon School, guys. 1 week left. You are almost done. Don't fail me now. Please. Alright. Bye, guys.